Let's look at this complex number here. Now this complex number is in polar form. Its modulus is 1 because a complex number in polar form has the form r cos theta plus I sin theta, and here r must be 1. So this complex number, which I'm calling z, is a point on the unit circle. That is a circle of radius 1 in the complex plane. Theta is measured anti-clockwise from the positive real axis. So I'm showing this complex number in this quadrant, but we could have it in any quadrant. We could have a point here, for example, and in that case theta will be an obtuse or a reflex angle. The coordinates of any point on a unit circle are given by cos of theta, sine of theta. When theta is an acute angle, then it's in this quadrant. Both cos of theta and sine of theta are positive. But if theta was an obtuse angle, say our complex number is in this quadrant here, then the cos of theta will be negative, because the x value of this point, or the real value, is negative, and sine of theta is positive. If our complex number is in this quadrant here, then both cos of theta and sine of theta are negative. And if it's here in this quadrant, cos of theta is positive, sine of theta is negative. So this all goes back to the trigonometry of the unit circle. Now let's look at 1 divided by z. We have essentially two complex numbers here. We have the complex number 1 plus 0i on top, and the complex number cos theta plus I sin theta in the denominator. And we want to write this as a single complex number. Now in a previous video I explained how to do division of complex numbers. What you do is you multiply above and below by the conjugate of the denominator. The conjugate of the denominator is got by changing the sign of the imaginary part. So the imaginary part of this complex number is actually sine of theta, and we change its sign, so the imaginary part becomes minus sine of theta. The notation for the conjugate of z is z bar. The reason we multiply z by z bar is so that we get a real number in the denominator. What will happen is that the I terms will cancel out. So on top we get 1 times cos theta minus I sin theta. Underneath we get cos squared theta plus sine squared theta. When we multiply a complex number by its conjugate, we get the modulus of the complex number squared. Just to prove this in general, if z is any complex number x plus yi, then z bar is going to be x minus yi. Z bar is the conjugate of z. So we have x times x is x squared. We have x times minus yi, that's minus y xy I. We have plus yi times x. And finally we have plus yi times minus yi, that's minus yi squared. These cross terms cancel out because we're multiplying expressions of the form a plus b times a minus b. So we end up getting a squared minus b squared. But since I squared is equal to minus 1, we end up with x squared plus y squared. But that's just the modulus of z squared. The modulus of z is the distance of z to the origin. So from Pythagoras' theorem, that's the square root of the real part squared plus the imaginary part squared. If we square that, we get z times z bar. So that's what we've done here. In our situation, x is equal to cos theta, y is equal to sine theta. So when we multiply cos theta plus I sin theta by its conjugate, we get cos squared theta plus sine squared theta. But cos squared theta plus sine squared theta equals 1 for all values of theta. This is a well-known identity. No matter what theta is, this denominator is 1. So we're just left with the numerator, cos theta minus I sin theta, which is actually the conjugate of z. So 1 divided by z is z bar. That's provided, of course, that z is a complex number with a modulus of 1. R is equal to 1 for this complex number. Let's plot z bar on this Argand diagram. So the only difference between z bar and z is the sign of the imaginary part. The real parts are exactly the same, but the imaginary part changes sign. So our complex number is in this quadrant here. It's got by reflecting this complex number about the real axis. So when we do that, we see that this angle here between this line and the positive real axis is theta. Its magnitude is 1. We haven't changed that. When we reflect this point through the real axis, we get a point on the unit circle. But look at the coordinates of this point. Well, this is the number cos theta minus I sine theta, so the coordinates are cos theta, comma, minus sine theta. But what we want to do is write this point as cos of some angle, comma, sine of some angle. Okay, and that angle is measured anti-clockwise from the positive real axis. So if I call that angle A, then we know from the trigonometry of the unit circle that the coordinates of this point are given by the cos of that angle, which is A, comma, sine of A. That angle must be measured anti-clockwise from the positive x or real axis. However, the positive angle A, which is a reflex angle, an angle between 270 and 360 for this particular z, is equal to minus theta, where minus theta is measured clockwise from the positive real axis. So for example, an angle of 325 degrees is equivalent to an angle of minus 45 degrees. Or sorry, minus 35 degrees. So when we say plus 325 degrees, we're measuring anti-clockwise from the positive real axis. When we say minus 35 degrees, we're measuring clockwise from the positive real axis. These are equivalent angles. So we can say that angle A is equivalent to minus theta. So we can replace A with minus theta. So that means we can rewrite our complex number. Cos of theta is equal to cos of minus theta. Minus sine theta is equivalent to sine of minus theta. So I'm replacing minus sine theta here with sine of minus theta. So this complex number here is also cos of minus theta plus I times sine of minus theta. These identities for negative angles are often given in tables, so you can just look them up. The cos of minus theta is cos of theta. The sine of minus theta is minus sine of theta. So this is an important result which I've highlighted here. Now let's look at the division of two complex numbers. We have the complex number z1 in polar form. Its modulus is r1, its argument is theta 1. We have a second complex number z2, its modulus is r2, its argument is theta 2. We want to divide z1 by z2, and we're going to use this result here. Well, we can factorize this thing out. We can factorize out r1 over r2, we can factorize out the numerator, and then we can factorize out 1 over the denominator. But of course we can now use this result up here for 1 over cos theta 2 plus I sine theta 2. We see that it's going to equal cos minus theta 2 plus I sine minus theta 2. Now the next thing we can do is use a result from a previous video for when we multiply two complex numbers together. So we're multiplying this complex number by this complex number here. Well, we multiply the arguments together. Well, the arguments of both of these underlined complex numbers are 1. Because these complex numbers are points on a unit circle. The distance of them to the origin is 1. So that's just 1 times 1. And we add the arguments. So that's what we covered in the previous video. So the result of doing this multiplication is cos of this argument theta 1 plus this argument here, which is minus theta 2. So we get theta 1 plus minus theta 2, or that's just theta 1 minus theta 2, plus I sine of the sum of the arguments. So we have theta 1 plus minus theta 2, or theta 1 minus theta 2. So that was covered in a previous video where we showed how to multiply two complex numbers that are in polar form. We simply add the arguments. So we've arrived at an important result for the division of two complex numbers which are in polar form. So to divide z1 by z2, we take the argument of z1 and divide by the argument of z2. So that's r1 divided by r2. And we subtract, or sorry, we divide the moduli. The modulus of z1 is r1, the modulus of z2 is r2. So we divide r1 by r2, and we subtract the arguments. So we take theta 1 and subtract theta 2. So this becomes the argument of our new complex number.